Hi and welcome to today's video. Today we'll be discussing the electric field created by a uniformly charged plane surface. It's going to be an amazingly short video but filled with complete steps as to how do you find it and the concepts behind them. Okay, so first things first, we're talking about a uniformly charged plane, right? A uniformly charged plane, the meaning of that is that the charge on that plane is sitting at equal distances from each other and it's not lumped at different places. That means if I make a plane like this, and this is a 3D diagram, but obviously in 2D it becomes difficult to make, but think of it like a piece of paper kept this way 90 degree from you, and the charge is distributed equally along the surface, so that every part of the surface has equal amount of charge. When this happens, we say that there is a surface charge density. Surface charge density of, say, sigma. Okay, of, say, sigma. So surface charge density is nothing but charge per unit area. Charge per unit area, because area will be the unit that we will be looking at, right? So once we have the surface charge density of the plane that we are talking about, now let's understand what is the next step. If we make the axis, I'm taking this as the x-axis. Obviously at 90 degree this becomes my y-axis, and there will be a z-axis coming this way. Now for y and z axis, will there be any electric field? No. Why not? Because the charges are completely in this field. Now the electric field along this YZ plane will be 0, right? Because that is where the plane resides. The electric field would be before, that means in the positive x direction as well as in the negative x direction. This is the negative x direction. So it will be in front of it and behind this plane. That's why the electric field will only be in this area or in this area and not in this plane, YZ plane. It won't be there. Okay. Now once we figure that out, once we've understood that concept, now we need to create a suitable Gaussian surface. Now a Gaussian surface is something that we choose to make, right? I have multiple options here. I can make a cuboid, I can make a cube, I can make a cylindrical, I can make a cylinder, right? The reason being because there is no electric field perpendicular. Why is there no electric field this way? Let's understand this. Why is there electric field only perpendicular to the surface? Because if an electric field is this way, that means it is along the surface, the charges will start moving. As soon as the charges start moving, it is not a static position. It becomes a current, it becomes a problem of current electricity, and we are not dealing with that right now. We are only talking about the static. We are only talking about the situations where charge is static. That's the reason why there is no electric field in the YZ plane. Now when electric field is only this way, then I can take a Gaussian surface I'm making a cuboid. Obviously it will be both ways. like this. It's difficult to see, but you'll understand the area that I have taken. This area in the middle is area A. Okay, so now the flux, all the flux is going to move only through this area as well as the backside area, because there is no electric field in this plane, in this axis. Therefore there will be no flux going from up or bottom, or even from all of any of the sides. So only this and this face will have the flux moving outwards. Now we'll use Gauss formula, Gauss law, to get our flux. Flux is simply electric field, which is what we want to find, into the area passing through it. Now there are two, where is the flux moving from? This and the back side. So this is the positive side. Why am I taking this positive? Because by convention we usually take x-axis as the positive side, but here also we can choose. So in this case I've taken both the electric field, I've taken the positive x-axis as the positive side. Therefore the electric field is also positive in this side, and the area is also positive. I will add the flux from the back end. The electric field is negative. Why is it negative? Because the direction of electric field is opposite to the first one that we have taken, and the area vector is also negative because it is opposite to the first one that we have taken. So now we have, when we simplify this, it becomes 2E into A as our total flux. This total flux will be equal to what? This will be equal to charge that is enclosed in it. How much is the charge enclosed? The surface charge density into the area. So it will be sigma A upon epsilon naught. This gives me electric field as A and A gets cancelled, and I will be left with sigma 2 epsilon naught as my electric field by a uniformly charged plane surface. Okay, now this is a very important result. The most important thing about this result is that it does not depend on the distance. That means the electric field does not depend on the distance. The electric field over here is also the same, and here is also the same. So the distance from the plane is not a factor in the electric field, which is very important. Now another important thing to remember is this is only true for an infinitely long plane. Okay, because when the plane becomes finite, that means if there is a metal sheet, obviously finite in dimensions, then this becomes a little distorted, especially at the edges. But in the center, when the metal sheet is huge and we are only talking about a small part in the center, then also this formula works. Okay, so this is the important thing, and this is the result that we get for electric field for a uniformly charged plane surface. So I hope you liked this video, and if you did, please do like, subscribe and share this video with your friends and discuss these concepts in detail. If you want me to pick up any other topic, please do comment in the comment box below so that I know which topics you want answered, and I'll make the videos as soon as possible. Do hit the notification bell so that you know when our next video is coming up. That's it for today. Thank you for watching.